So we just finished this part 1 of the activity, how to track the object, and we want to go back to our main dashboard page. So then looks like we're analyzing height versus time, and height is y. So let's see. So we opened up the CSV, got that set up, and now we want to make a scatter plot. So, and we want to ask things like, how does the height change over time? Let's ask the question like, do we expect a linear change in y over time or some kind of curve? We got our data uploaded, and now we're looking at it here through Google Sheets. And we got 3 columns, 3 different key information. We have T over here, just slide through. It might be hard to see. T for time. We got X, that measured the object's position horizontally and along the X direction. And then we got Y here, representing its position in the vertical direction. And then one thing to remember in our video is that for time, this is seconds, because our video was in frames per second, and specifically in that particular video of the red ball, it is 240th of a second. And that's why its time starts here at 0 for the first frame, and then this here is the first 240th second, and as it progresses. Then as well, if you remember when I talked about the little right rectangle in our tracking software, that was to reference the meter stick that was on the floor, and so the units of measurement for X and Y are in meters, which it's in science and physics particularly, it's good to know what units you're working with, otherwise things aren't going to make much sense. And then here you might be wondering, why does it say object out of range? This is because if we go back to our tracking software, the tracker the STEMcoding tracker we were using, we set up the green borders here. And so the tracker is only tracking when things are within the green borders. And so, for our first few frames, there's nothing in within that region. So you can see here, we got the very first few seconds of seconds. And that's what this object out of range is, which is good. So there wasn't some magical flying red ball before it even got into frame. And so we'll scroll down to our very first actual data point here. And now, it looks like at the 0.15 seconds, or it's not even a second yet, but it's that good. We have our first measurement in the X direction, the X position of our object, and then we have the Y position of our object. And if we scroll down, we can see as it changes over time. It's always good just to take a look at your data. You never know, it could be something that's just weird, but right now it looks pretty reasonable. A nice way, this should work on Excel or on whichever sheet service you're using, but on Google Sheets, if you click on the very first row and on the leftmost side, and you scroll all the way down to the end, and you hold the shift key before you click. You hold the shift key on your keyboard, click, it'll highlight all the data between the first and the last click. So just to show you, we highlighted all our data, and then go to insert and chart, and then boom, we got ourselves a plot. Google doesn't really distinguish which represents X and which represents Y, but that's a good exercise. Let's just think about it. So we had a ball, and we threw it in there, ball in the scope, and it makes sense in the X direction. It's only ever moving this way. There was never it didn't come back at us. It didn't break the laws of physics. So if you just think about a ball in its curved nature, the curve, how it moves up and down, that's all height, and so we can deduce that this curve here represents the Y position, because it did at one point start high and then it fell to the ground, so it started getting lower. Versus here for the X position, it just kept getting further away from us, so it would make sense over time the X position would go further away. So it makes sense that the curved line would represent our height, the Y position, and not this the linear blue line here. And another good thing to test anytime you plot something is just, does it make sense? Because we did just use like an automated feature here. Like, does its starting point, does it actually resemble our data? It's always safe to check, make sure there's no error. So, we're saying this blue line is the X position. So it looks like it starts somewhere, maybe it's like 0.7, 0.75. And this is the earliest time that we have the data for. And then similarly, for the Y, it starts, maybe it's like a little less than 2.5. And so now let's go back to our data. And here, remember, this is time. The middle one is the X position, and then the rightmost one is the Y position. So it does look like our initial position checks out with our plot. It's somewhere about 0.7. We guess 0.75, but it's 0.728. It's pretty good, checks out. And then similarly for the Y position, it starts where the first data point is supposed to start at 2.4. All right, so now, we're only for this part of the activity, we're only interested in the height over time, so the Y position. We will later begin to consider changes in X and like acceleration, velocity, and things like that, but that'll be later in the activity. So let's clean up our chart and let's get rid of X. So if you clicked out, you just hit the 3 dots top right, and you can't see it. So you hit the 3 dots on the top right here, and then there's an edit chart button, and it should bring you up here. So here it tells us about the X-axis, the data of the X-axis, that's fine. And then now this thing that says series, this is just talking about the items that are labeled for the Y-axis. And so in our case, B here, this represents the B column, which represents the X position for us. And so that's the line we want to get out. And so you go ahead, hit these 3 dots, and then I think you just hit remove, and then there you go. Now we just have our plot that's focusing on height and over time. So there's other cool things to do in this tab. Firstly, I want to switch to a scatter plot because that's kind of more representative. Even though we did get really nice frames per second, this is probably still going to look like a line. But in essence, if you had 60 frames per second, having a scatter plot will be more beneficial for you than having a line. So in this case, I went to scatter. It looked pretty much the same, but that, as I said, that's because we had 200 frames per second. So there was no really ever any gaps in time. So we got a really nice line here. One thing to make sure that I say X-axis because that's just how you talk about in a chart, and Y-axis. Let's see, Y-axis here, and this time, or this the X-axis, but the X-axis here is representing time. It's not representing the X position at all, the X coordinate. This is just saying X-axis, and I'm referencing time. And as well, look at these numbers here at the bottom. They go from about like 0.2 all the way, maybe as far as like 1.2. It's just doesn't have a tick mark. It's clear that it represents the time column, because as you can see, our values of our time, when you look at it, goes from 0.15, and then if we scroll all the way down to 1.2 almost. This one. And so, just to justify some more that this is for definitely a time versus height plot. So let's make a little more edits to this plot that we have here. Google automated this when we started our plot, and this is just not accurate or representative of what's actually plotted here. So let's make some cosmetic changes, and I'll go through that with you just to see, because you will more than likely have the same thing. And so you hit the 3 dots here, edit chart, and then on the top right bar there's customize, and then in chart and access titles. And so now instead of X and Y, this is actually a plot of height and time. So the height, and then we'll say, versus the time. And then, let's just throw the units on there. It's just good, it's some good plot. If you're going to share this with someone, that'd probably be the first question if they didn't ask what units. So we'll just throw here All right, so now we got our title. As you see as well, we don't have any label here to describe what is even the y-axis representing, so we could add that. Then as well here, we know this is time, but maybe we want to be more descriptive of it as well, so we'll clean that up. So if we go back, you click this here, this is chart title, and now let's change the horizontal axis. We'll set time, put the units there, and then we go vertical. And we're going to put Y for this one because we know it's Y position, but we could keep the title as height. But you're also welcome to name it as you please. Now we got plot set up, or it looks correct now. So perfect, height versus time, and height is represented by Y when it's in meters. Then as well we got, it's clear now, time in seconds. And now this is a really pretty plot that we made. We got it all set up here, and now let's go back to the activity page just to see what's next, or what maybe there's some questions we need to answer. So we go here. So we made our scatter plot. How does the height change? It goes down thanks to gravity. The ball falls, and it makes sense that we saw a curve because the ball went up a little bit and then it came back down. Now does the plot look like how we expected? Earlier, I did kind of talk about it with y'all, and it does make sense that we threw a ball slightly up and then it would curve, it come down. And then what type of function, what type of function does it resemble? This is a very good question. We'll kind of touch on this on the next step, but just think about it. So it's not linear, so it's not a straight line, so it's not something times x, so it's got to be something else, but we'll come to that one. All right, so now we want to fit a trend line on our data. Trend lines are useful because sometimes there's something underlying, some underlying physics, or just there's a relationship that can describe the trajectory of the ball. In this case, since it's position over time, so we could kind of see where would it be after another 10 seconds. Using this trend line, this would be a relationship, and we could figure that out. Assuming there was no floor, probably the ball would hit the ground, but let's just imagine there wasn't a ground. It's all right. We're going to go back to our Google Sheets now, and let's fit a trend line. All right, and so we're back at our chart here. We're going to be using this here to add the trend line. You could go customize, series. And series is just representing what the Y, what our height position is. This is just that's what it's representing. And then you see down here at the bottom, it says add trend line. So go ahead and click that. So cool, we see that we get it just auto-filled. This does it by default. I'll do it with any data set. It's not unique to this data. Google didn't guess that linear is the best way. Put linear. It's just a feature of what Google Sheets does, and it may be similar with other software, other programs, but this is what Google Sheets does. So don't be confused at all. This is just how it does once we add the trend line option in here. How about, what if I just move this so I don't need to keep moving? We live in the future, this technology. All right, so we hit add trend line, and like I stated earlier, this shouldn't be linear, right? Because it goes up, then it came down, and as we can see here, obviously there's a curvature nature there. So let's see. So we got other options. We got exponential, got polynomial, logarithmic, power series, a moving average. So in this case, we're just going to pick polynomial. It's going to have some polynomials. I'll go ahead and click. Oh, there we go. Go click it. This means we would have an equation that might have an x future plus x something times x squared, and up depending on how many polynomial degrees, could go to cube to the power 4 or 5. In this case, we'll just do 2, and then let's make this trend line different from this. So an issue you might find is, where'd the trend line go? Watch, let me see. We'll go back to linear. Okay, it's there, and then I go to polynomial, second degree, and now it's gone. But Might be hard to see on here, but there's a tiny red tick right here. So this is just a plotting issue that Google Sheets had that I kind of just found when doing the exercise. So a way to kind of see the trend line is you want to go make the opacity of the line, make it 100%, make it like, that just means is it transparent or not, and you don't want it to be, and then go back up and then now change the opacity of the actual scattered data points and make it like, might be hard on screen, let's make this like 10%. So now this is just the unfortunate part of Google Sheets, but you can see our data points are still there. They're just a little more transparent, so now we can actually see the trend line fit all these scatter points here. So, and you can see this is almost this is some good data. This is like a perfect fit. But sometimes, just in general, if you have a perfect fit to some random experiment data, you just always gotta be careful. But this is a controlled exercise. We know that this is what is expected, so this does check out. So there we go. We can see our trend line. And then as well, if we scroll down to the customized thing where we set up the degrees and everything, there's this label. And this is what we want to see so we can see the equation that it makes with this trend line. So then you can see over here, it auto-populated and it made the line of best fit that best fit our data. And now this will answer some interesting things. We'll refer back to the activity sheet, but it looks like an equation that is negative 4.76x squared plus 4.54x plus 1.87 is the best best function that represents our data. And something as well, I know it says x, this is just standard, but remember that for x, it's meaning the x-axis values, which for us refers to time. So in essence, you could replace the x's here to make sense to you to be t for time, which would be in seconds. So, I'll just restate 4.76 times squared plus 4.54 times the value of time, and then plus this constant 1.87. And let's go to our activity sheet here. And then, nice. As you see, there is, we're going to infer what the y acceleration is using the trend line equation. And so the nice thing, there's kinematic equations that I believe by this time you should be aware of what these kinematic equations are, but there is one that can represent position over time, and then you get this equation here. So if you look at it, we get the form that we had in our Google sheet that we got, because we said it was polynomial. So we see that we have 1/2 times acceleration in the y direction t squared, and then similarly velocity times time, and then this constant here. And so now, maybe pause the video and just think about it. Okay, so we want to know what the acceleration is. So it looks like this quantity would be of interest. How would we get the acceleration here? Utilizing the equation that got best fitted here. And so I'm just going to write the equation that the trend line found for us based on the trend line through our data points. And so this is the function that we got. And now if we go back to the activity page, we're able to infer a few things. So as you're aware, there's kinematic equations that help kind of represent velocity or position over time through things like its velocity, its acceleration, its position. And the kinematic equation that we're interested in, that is a list that is written out in your activity page, is the following. So it has, right at the same color's fine. Some general. This equation is I for y initial plus velocity in y times t, just time, plus
1/2 acceleration y squared.
All right. So this is our kinematic equation here, and this is the equation that our trend showed us. This is the function that our trend line gave us that represents our data. And so you kind of can see some relationships here by looking at it. Looking at all the terms. This t squared here is the same as here, and then this t here is similar to this term that's got the t, and this is just a constant here. And now we're able to identify key information about our object as it moves throughout time. So this term here tells us about the initial position in the y direction, in the y position of our object. So let's just write it down here. And that'll be equal to 1.87, which you can go look and justify yourself. If you just go back and look at your data, the very first data point, you should be able to see that its intercept with the y-axis, like when the line reaches the axis, it should be 1.87. And then here, this 4.54 is the initial velocity of our object. So I'll write that down over here.
Sheets of 4.54.
I believe we will be using this later, so write these down, have them somewhere. But as the step says, we're trying to figure out what the acceleration is, which we'll get to here. And so now, following the same logic we've been doing, 1/2 ay, the acceleration y, should be equal to that of negative 4.76 t squared. And then we can then solve for what the acceleration is. So I'm going to move a little here on the right just so we can see. So I'm going to go 1/2 ay, and it should be equal to minus 4.76. Now this is, hopefully you got to this math level to solve this, but if not, I got you. So we have this 1/2 here. Now we just need to move it, or we need to multiply both sides by the half to then isolate and just get the acceleration. So, multiply the whole thing by 2, and then we'll get a y. So you put minus, and then I'm do big brain math here, and I'll get 9.52. All right, so here's our value for the acceleration. We got negative 9.52, and the nice thing about this, this tracker problem here, particularly acceleration y direction, is we actually know what the real answer should be, the expected answer, and that's thanks to gravity, because any object that falls and then in this space feels the effect of gravity, and we know this by heart, or if you're just now learning, you'll soon know this by heart. But the gravity, the gravitational acceleration, which I'll label as g, and I'll round a little bit, but it's negative 9.8, and this is very close to the value that we got. And now let's just think, experimentally, it's probably pretty justified that we didn't get it perfect, because there was just conditions in the video or in the experiment. If you put your own video in the experiment that you do, is things to consider in regards to the video. So one thing is, if your camera was at somewhat of an angle, the data we got is now, it's somewhat incorrect, or it's somewhat skewed in the sense that it's actually affecting the true value of its y position given how the camera is positioned. Or it could be that in the video the meter stick was way closer than the camera versus where the object and the person who threw that basketball was actually further away, and it could affect it with the recording mechanisms of the tracker on how it got positioned. Alright, and before actually I take off, units. This is a big no-no, is if you have data, it's got to have units. They got to mean something, because if I don't have any units here, these are just numbers, and what does it mean? And so let's just go write our units for these variables that we calculated. So this is initial position. And as if we remember, we use the meter stick for reference for this data, so this should be represented on the meter. So, now this is a velocity. This is distance over time, and we know that for our time, it was in seconds, and so this should be meters per second. Now acceleration. This is how the velocity changed over time, which then gives us meters per second squared. And we got to do the gravitational constant justice. It is also an acceleration, and that is meters per second squared. All right, so this is the final product here. Got all our units on the board. We got all our values, and this will be the end of this part of this video where we're looking at height versus time. But now we want to answer some questions when we look at velocity versus time, and that'll be in the next video, and we'll be able to deduce and figure out some other cool physics questions there. So hopefully y'all tune in and y'all check that out, and it'll follow very similar. That will be part 3, and when you look at the activity pages to follow that. All right, hope y'all have a good one. Let's go do some physics. I don't know.